Hi, I'm glad to present our work entitled Task Conditioned Adaptation of Visual Features in Multitask Policy Learning. Alright, can we have a general vision model for robotics? This is an important question. A common approach to this often includes two steps. First, pre-training a vision model on diverse visual data. An example is VC1, a vision transformer pre-trained with masked autoencoding on a large visual dataset composed of 7 sub-datasets, mainly biased toward egocentric vision. VC1 is the main vision backbone we will be using in our work, but our supplementary material presents experiments showing our method generalizes to other backbones such as MVP or PVR. Once the vision model is pre-trained, previous work generally trains one policy for each robotic task of interest, encoding visual observations with the frozen vision model. This is done with behavior cloning in VC1. We can then ask ourselves a few questions. First, visual features will likely depend on the task to solve. Can we adapt those features based on the task at hand? In this work, we introduce task-conditioned adapters to modulate the visual features from a pre-trained vision model. Then, instead of having a specific policy per task, could we have a single multitask policy? We train a single policy to solve 12 known tasks from 3 benchmarks: ADROIT, DeepMind Control, and MetaWorld. This is called the known task setting. Going further, a general policy should not only be able to tackle a set of known tasks, but also adapt to new tasks from a few demonstrations. We thus study the adaptation of our approach to new tasks without modifying any neural weight, only optimizing what we will later refer to as the task embedding. This is done on 15 new tasks from the MetaWorld benchmark, and this setup is called the few-shot setup. Here is an overview of the method. You can see here the policy queried on the 12 known tasks at test time. We can also provide a few demonstrations of new tasks, such as this faucet opening task. We can then optimize a task embedding that will be used by our visual adapters to modulate visual features fed to the multitask policy. Finally, we study how our policy can be adapted to these 15 new tasks from the optimized task embeddings. Let's now look at the approach. This is what was previously done, except that we have here a single policy for all training tasks. The vision model is frozen and only the policy is trained with behavior cloning. In this work, we add visual adapters, simple MLP blocks, either inside the model, we call those middle adapters, or after the model, we call this one a top adapter. However, such adapter modules have already been studied in transformer-based models. Our contribution is thus to condition such adapters on a task embedding, which should contain information about the essence of a given task. After training, we may want to adapt our model to new tasks without any fine-tuning. Here comes our task embedding optimization procedure. All weights are frozen, a new task embedding is initialized and optimized to minimize the difference between predicted actions and expert actions from a few collected trajectories, 5 trajectories in our experiments. At inference time, we can either use one of the 12 learned task embeddings if the task is known, or an optimized task embedding for a new task. Let's move on to experimental results. Here is the average performance of our method without adapters on test episodes of the 12 known tasks. Adding middle adapters without task embedding improves performance. Middle adapters conditioned on task embeddings lead to a boost in performance. Adding a top adapter improves, again, performance. And conditioning the top adapter on the task embedding leads to the best performance. If we now look at per task average performance, we see that using task conditioned adapters leads to higher performance and that our method is competitive with specific single task policies. Finally, we show the average performance of our method on the 15 new tasks. As can be seen, our method is able to adapt relatively well to most tasks, while it is important to keep in mind none of these were present in the training set. We can thus adapt to new types of objects and dynamics. Alright, I'd like to thank you for your attention, and I'll be happy to answer any question by email. Thanks.